I think we'll give it like 30 more seconds. See a bunch of people popping in. I think we can go ahead and get started.
Okay.
All right, hello everyone, welcome back. It's my pleasure to introduce Professor Jim Eisenstein. Professor Eisenstein received his PhD from UC Berkeley and worked at Bell Labs for many years before becoming a professor at Caltech, where he is now. He is well known for his experimental studies on the transport properties of low-dimensional electron systems and much more. And today he will tell us about exciton condensation in quantum Hall bilayers. Take it away, Professor Eisenstein.
Okay, thank you. Let's see if the sharing works the way it's supposed to. Okay, hold on one moment. All right, everything good? All right, great. Right, so thank you very much for the invitation to do this. I'm delighted. I've going to give an experimental talk or talk about experiments. Maybe it's also an experimental talk, I'm not sure. Actually, I'm going to give two talks, both of them about experiments related to exciton condensation in quantum Hall bilayers. And you'll hear in the next talk, Professor Halpern is going to talk also about bilayer systems from a theoretical perspective. So if you have any really hard questions, you should certainly send them to him, not me. I've been at this subject for a long time, really since about 1990. So it's been, maybe some of you aren't even that old. Probably many of you aren't that old. So I've been working on it on and off for a long, long time, as have many other people around the world. There's been a lot of experimental activity, which continues today, especially with the advent of graphene and multi-layer graphene materials. And there's been a humongous amount of theoretical work, which you can look into if you like. I'm not going to say much about that or try to give you any kind of historical point of view on it. It's much too vast for me to do that. But I'd like to nevertheless give you a flavor for what the interesting physical phenomena are related to that we call exciton condensation in quantum Hall bilayers. So that's going to be the emphasis of the talk. It's going to be on what you actually see when you do an experiment on these systems. And I'm going to start with a cartoon. Well, here's my cartoon. And I think this is going to, if you can follow what I'm saying about this cartoon, you'll understand, at least from my point of view, what the most interesting phenomena really is. So imagine you have some material of some kind, and it's orange in this case, and you make some electrical contacts onto it with a soldering pencil or some other means, evaporation, what have you. And you try to do what we commonly call a transport measurement, which is to drive some electricity through the sample and see what happens. And you find that for this material, nothing happens. No matter where you put these contacts, no current flows. So you write down in your lab notebook, this material is an insulator. Now, then you go on a little bit, maybe even by mistake, and you inadvertently short circuit two of the other contacts you might have made, or some other pair of contacts somewhere else on the sample, maybe on the same edge, maybe not on the same edge, but you have two other contacts which you connect together with a wire. And to your surprise, you see that your ammeter shows that a current is now flowing, whereas before it wasn't. So what's going on? This is a pretty strange insulator that would do this. Well, at least one way in which this can happen, and such materials can exist, is if they contain mobile excitons, charge neutral objects that can go across the sample in some way. Let's not worry about how that happens. They're neutral. They get generated by the source, which in this case is over on the left, and travel across the sample and recombine, or if you like, ionize on the other side of the sample and drive current through that other wire. And if it weren't for that other wire, that other connection, you'd go back and still be in the situation in which you thought no current was flowing and the material was an insulator. So yes, it's an insulator in certain respects, but it's also a conductor in certain respects. So that's what an exciton condensate can do for you. And that's what it's exactly that phenomenon that I'm going to illustrate in the talk today. So how do you get one of these things? It turns out that, I mean, people have been searching, I should say, from a historical perspective, people were searching for exciton condensation really since shortly after the theoretical understanding of superconductivity in the BCS theory in the late 50s. Why not combine, instead of making Cooper pairs out of 2 electrons, why not combine an electron and a hole and have that thing be your object and Bose condense it and have some kind of exotic superfluid? That turned out to be and remains a viable pathway, but a very difficult one. It turns out that there's, in some sense, a much easier technique, one that has some advantages, and that's to start with a double layer 2-dimensional electron gas, whether it's in graphene or whether it's in gallium arsenide or in some other material, doesn't matter. And take these 2 layers of electrons and bring them close together. So close that, in fact, the Coulomb interaction between the electrons in one layer with the electrons in the other layer is roughly about the same strength as the Coulomb interaction between electrons that are in the same layer. So you should be able to at least envision making such a thing. And then add a big, turns out that the key ingredient here, because they don't have any holes yet, the key ingredient here is to put on a big magnetic field. And if you do this, and I'm going to say much more about this as time goes on, if you do this, bingo, the magnetic field is adjusted correctly, the system can be driven into a state which may be viewed as a condensate of interlayer excitons, in which an electron in one layer is tightly bound to a vacancy between the electrons in the other layer, or if you want to call it a hole. And I'm going to talk about that exact system today. All right, so where do you get these things? Well, one way to get them, of course, is to the way that I have used in my research is to start with a layered material grown by some crystal growth technique. We use molecular beam epitaxy to grow us 2 very thin layers of gallium arsenide separated by thicker layers of aluminum gallium arsenide on the outside, which is a larger bandgap material and forms a barrier. And then some other material also turns out it's aluminum gallium arsenide with a different concentration in a thin layer between the 2 gallium arsenide quantum wells. And then some, of course, you have to dope the system in some way. So there's some silicon dopant atoms put in to populate those green slabs with electrons. And if you do all that and you know how to make molecular beam epitaxy, you'll get yourself a 2-dimensional, a bilayer 2-dimensional electron gas. And that's the system that I will talk about exclusively today. I have no real knowledge about alternatives, one most prominent one being double layer or multi-double layer, multi-bilayer, even graphene, which has reinvigorated, I would say, on the experimental side enormously the interest in exciton condensation and related correlated phenomena in bilayer systems. But Professor Halperin will have much more, I think, to say about the graphene system than I do. All right. I should also, I think I already said this, but I should also give credit where credit is due to, there have been many, and I'm only talking about experiments here. There have been many experimental groups that have contributed to the understanding that we now have. And I'm, again, excluding graphene from this list. This is just the gallium arsenide based bilayer experiments done starting at Bell Labs, but also in von Klitzing's group at Stuttgart, at NTT in Japan, here in Princeton, or there in Princeton, in Australia, in New South Wales, and the work that we've done at Caltech in California. And probably there's some other ones that I'm regrettably not mentioning because I don't remember them. So just to refresh your memory from maybe even earlier this morning, two-dimensional electrons in magnetic fields is a playground for physicists like no other. You know that if there's no magnetic field applied and you have a clean two-dimensional electron system, it's a good Fermi gas, nice Fermi distribution, constant density of states in 2 dimensions. But if you put on a magnetic field, those electrons have to go around in circular orbits. Those orbits, of course, are quantized. And you probably, most of you have solved the problem, the elementary quantum mechanics problem of electrons in a magnetic, two-dimensional electrons in a magnetic field. And you know that the energy levels become discrete, whereas they were continuous without the magnetic field, and they're discrete levels. We call them Landau levels. There are also spin sublevels to these, but I'm not going to have much to say about spin today. These levels are highly degenerate. These Landau levels are highly degenerate. You can place those circles pretty much anywhere in the sample. So there's a degeneracy that's proportional to the area of the sample. And the important point is that if the magnetic field is high enough, all of the electrons in your material will be in the lowest Landau level. There's a large energy gap to the next Landau level. And so the only thing the electrons in that situation really have to contend with is their repulsion from the other electrons in the system. So the beauty of this is that in 2 dimensions, the magnetic field renders the two-dimensional electron gas, which might have been regarded as fairly weakly interacting at 0 magnetic field, to becoming extremely strongly interacting when the magnetic field is large. So that's what makes it a good system to look for correlation physics. You know about the quantum Hall effect. You've heard about this now already in other talks today and yesterday. Here's a cartoon. Nicely, not a cartoon. This is actually data. I don't know whose it is, showing the integer quantized Hall effect. Nice plateaus. As you know, these plateaus are perfectly flat, at least to within parts in 10 to the 10, 10 to the 11. I don't know what the current value is for their precision. And they are in fact used to define the ohm now. It is actually used as a method, a metrological standard for determining what the ohm is. These 2 curves in here, the red curve is the Hall effect, measured with the voltage transverse to the current flow direction. And the green curve is the longitudinal or the ordinary resistance that you might think of as you ramp the magnetic field. And wherever there's a quantized Hall plateau, there's a very, very deep 0 resistance state in the longitudinal resistance. And one tends to say that the system is dissipationless inside these quantized Hall states. It's a little bit of a misnomer because it's not really dissipationless. There's a current and there's a Hall voltage across the sample. So there actually is dissipation, but it's occurring near the source and drain context. But I'm not going to go into that minor detail. So if you make the sample better, meaning higher quality, you find out there's just a bewildering array of plateaus in the Hall resistance that are called the fractional quantum Hall effect. These occur when the Landau levels are partially occupied. And if you recall from the single particle picture that I mentioned a moment ago, these Landau levels were supposed to be discrete. So what happens when you have them partially occupied? There's many possible configurations the electrons can assume owing to their repulsion from their neighbors. And under certain partial occupancies, most notably 1/3 occupancy, which was the discovery of the fractional quantum Hall effect, when the lowest Landau level is 1/3 occupied, there's a special correlated state in which electron-electron interactions spontaneously create an energy gap in the system. And that energy gap plays the role needed to have a quantization of a Hall effect, and a Hall plateau is observed. And you can see in this picture, which is from a long time ago, 30 years ago, there's a lot of nice states in here, all kinds of fractional numbers on them. And you can see also, those are the fractional occupancies of the lowest Landau level. And you can see that right away that there's they all have odd denominators. Nothing going on in the Hall effect at filling factor 1/2, as Professor Alpern's already talked about. Hall effect is, linear, and it's smooth variation in the longitudinal resistivity, but it's certainly not going down to zero. So you might think nothing interesting is going on there. Nothing could be further from the truth. It's actually a fascinating system. And Professor Halpern has talked about that already. This is the regime of the so-called composite fermion fluid, or the composite fermion metallic phase at half filling. So there's no fractional quantum Hall effect there. However, if you have 2 layers, the electron gas, instead of 1, you find out that when you measure the Hall resistance, that lo and behold, there is a plateau at twice h/e², which means filling factor 1/2. Now, when you have 2 layers in these 2 quantum wells that I've got the cartoon of over here, the filling factor in the simplest case where the 2 layers have the same electron density, which is the only case I'm going to talk about, that filling factor of 1/2 is really 1/4 plus 1/4. So it makes matters even worse than you might have thought, that there was certainly no quantized Hall plateau at 1/4 filling of a single layer. But when you have 2 of them together, you have 2 1/4 fillings. If the layers are close enough together, they create a quantized Hall effect at half filling. Very interesting. We got very excited about this back in the early 90s. Breaks the odd denominator rule. Quite interesting. Not going to talk about it really today. But you can see also that there's a Hall plateau at h/e², which is filling factor 1. And again, since there are 2 layers there, this corresponds to each of those layers being at 1/2 filling. So in that situation I talked about, the single layer, there was no 1/2 filled quantized Hall plateau. Now, magically, when those 2 things come together, 1/2 plus 1/2 equals 1, a gap opens up and a Hall plateau forms. That's the situation that I am going to talk about. So it turns out that when those experiments were done, there was already theoretical arguments for why there might be such states, both at the 1/2 total filling 1/2 and the total filling 1 case. Here are some cartoons of wave functions of a class written down by Professor Halpern in 1983, the same year that Bob Laughlin wrote down the 1/3 famous 1/3 state for the fractional quantum Hall effect. Professor Halpern generalized that type of wave function to consider other cases in which there's a discrete internal degree of freedom. I don't know whether he was thinking of layers at the time, probably more spin. He can maybe elaborate on that if he wants to later. But nonetheless, he wrote down specific wave functions that might represent incompressible states of bilayer systems at other filling factors. And there was numerical evidence at the same time, or actually a few years later, that supported the possibility that these states actually would exist in experiment. Okay, so what is it that's so special about this nu=1 state? And for that, I put this cartoon up, which is to remind you about sort of a very elementary image of what the difference between a semiconductor and a superconductor is. So in a semiconductor, you have an energy gap that separates a band of electrons, a conduction band, from a band of holes, a valence band, and that's the gap that defines really a semiconductor. In a superconductor, you also have an energy gap, but it's a collective phenomenon. It occurs at low temperatures in a metal. But yes, you have quasi-electrons. Yes, you have quasi-holes. But more importantly, or equally importantly, you have a condensate that exists inside the gap of Cooper pairs. So there's something very different than about these 2 cases because of that existence of the condensate. The same thing is true in the nu=1 quantized Hall phase in bilayer systems. An ordinary quantum Hall effect, whether it's fractional or integer, you have 2 bands separated by an energy gap. Either it's collective or it's an integer quantum Hall gap. But in the nu=1 bilayer quantum Hall effect, you again have an energy gap. There's a Hall plateau after all, and a zero resistance state, but there's a condensate of excitons. And this was something which I don't know the degree to which it was appreciated in the early days when the theoretical ideas for the existence of such a phase, such a Hall plateau might exist, whether it was really appreciated that there was this condensate and that it could have exotic properties. And it's that I want to talk about. So let's go back a little bit to some simple physics. You might, if you're thinking hard about bilayer systems, you'll remember that if you have two quantum wells, you can always have tunneling between those two layers. And if there's tunneling between the two layers, electrons can occupy symmetric and anti-symmetric combinations of the two layer eigenstates. And in fact, if the tunneling is sufficiently strong, two layers that are half filled really look like one layer of symmetric electrons because the tunneling is really strong. And that would provide a very simple a simple explanation that does not require strong electron-electron interactions to explain the existence of a nu equal one quantized Hall plateau. That's not the explanation for the physics I'm going to describe, but I will have more to say about it. Instead, there's also a way to create a gap that has nothing to do with tunneling or exists in the limit of zero tunneling, and that's this exotic so-called exciton condensate, or some people like to call it the 111 state, at least in the limit of closely spaced layers. So some experiments that were done at Bell Labs, a postdoc of mine, Sheena Murphy, we looked at many samples where we made systematic changes in the geometry, the thickness, the height of the barrier, so on and so forth, and tried to decide, made measurements to indicate whether the sample showed the quantum Hall effect, the bilayer quantum Hall effect with H over E squared Hall plateau or not. And the blue dots in this diagram, and I'll explain what the diagram is in a minute, are samples which did not illustrate such a plateau, and the red dots are ones that did. What are the two axes? Well, the vertical axis is the spacing between the layers in units of the magnetic length to make it dimensionless. Because that's, after all, that's all that can really matter is that ratio. And the horizontal axis is the strength of the tunneling, which I told you about, because there could always be tunneling between the layers. And that's been normalized by, there's a division mark missing here. That's been normalized by the mean Coulomb energy. And what this experiment showed was that as the tunneling was reduced, the phase space for the red samples went down, but then it stopped going down, meaning that as far as we could tell, the phase boundary intersected the vertical axis at finite layer separation. That's a key point. In the limit of no tunneling, it was still possible to have the nu equal one Hall plateau, even without any tunneling. That's what this experiment seemed to indicate. And what I'll be talking about today entirely deals with what happens on this vertical axis. In other words, in the limit of zero tunneling. I'll have to tell you more about what I mean by that. What I mean by zero in that case. So there's some kind of diagram, some kind of phase diagram where if I eliminate all the many variables it can depend on and only concentrate on separation between the layers, somehow if the layers are far apart, the system behaves like two half-filled Landau levels that don't talk to one another very much. Whereas if they're close together, they talk a lot through the Coulomb interaction and open a gap and have a Hall plateau. And there's something like a quantum critical point. And there's much discussion about, is this really a quantum critical, is this really a quantum phase transition? If so, what kind? That's really an open problem. And I hope that some of you students out there will have a look at this and figure out what's really going on, because it's not fully understood. So here's what I mean by zero tunneling. We can make, this is the same graph, by the way, but I put it on a logarithmic axis of tunneling so that you can see what I mean by having a small tunneling strength. We can make samples with very tall barriers, and we can produce samples which are like this yellow dot, which are sitting over here with a number called 10 to the minus 7 down at the bottom. That's the tunneling strength, or the splitting between the symmetric and the antisymmetric state of the double quantum well in units of the Coulomb energy. But 1 part in 10 million. Okay, so I mean, we can't make it really zero, but we can make it darn small. 1 part in 10 to the 7th or so. That's symmetric antisymmetric splitting around 10 microkelvin. Very, very tiny. So we really are in the limit of extremely small tunneling, never zero. By the way, we want, as an experimentalist, you can probably imagine it's a difficult process and very time consuming and very frustrating to have to make sample after sample after sample to figure out what the heck is going on. It's much better to take one sample and find a way to tune it around inside the phase diagram. And it turns out you can do that with electrostatic gates. And what we will do throughout the talk is make adjustments to these electrostatic gate voltages so that the electron density in the quantum wells are always maintained to be equal in the 2 layers, but is changed continuously. And then I adjust some magnetic field, some knob on my power supply, my magnet, to always render the system at filling factor 1. So I can move on that dashed line with a single sample. Very important to be able to do that. It's extremely difficult otherwise to construct such a diagram. In that limit of very, very small tunneling, the quantum Hall effect, here it is. This is not the Hall plateau. This is the longitudinal resistance showing a very deep minimum, even though the tunneling is a part in 10 million of the Coulomb energy. The energy gap, which can be estimated from the temperature dependence of the resistance in that regime, is a fraction of a Kelvin, a third of a Kelvin, orders and orders of magnitude bigger than the symmetric antisymmetric splitting. So this is absolutely in the strong Coulomb limit. All right. So what's going on? So there's more than one way to think about this condensed phase. And in fact, I'm going to talk briefly and more actually tomorrow a little bit about the ferromagnetic picture. It turns out that the relevant idea here is that electrons in the bilayer system, when they're in the condensed phase, essentially lose their memory of what layer they are in. And this happens spontaneously. It's a symmetry breaking. The electrons decide, if you like, collectively, that they want to be in essentially equal probability in the 2 layers. Equal probability with some phase. This is ferromagnetism. This phase, phi, tells you the direction of the pseudo-spin. And by pseudo-spin, I mean blue electrons in layer number 1. I'm going to call, this is not real spin, pseudo-spin is pseudo-spin up, red electron pseudo-spin down, and I can make a ferromagnet out of that by aligning everyone. And the alignment that is relevant is that all the pseudospins lay in the XY plane, all with the same phase, phi. That is what sometimes is called spontaneous interlayer phase coherence. And this phase is something which we can actually, in fact, the phase is in many ways the critical variable. We will talk a lot about that. All right, so that's one way to think about this, is exchange ferromagnetism. That's one way to think about the condensed phase. Alternatively, and I think for many purposes more intuitively, you can think about the system as this exciton condensate. That's what seems to be most people's choice of language these days. The 2 layers are each half-filled Landau levels. I can choose to think of one of the layers as a half-filled Landau level of electrons and the other layer as a half-filled Landau level of holes plus a fully filled Landau level. This is quite analogous to a semiconductor in which you talk about the valence band and talk about holes in it when you're really thinking about the absence of the empty electronic states in the valence band. In that picture, the wave function, if you like, in the limit of small layer separation looks very much like a BCS wave function for a superconductor with some differences, but basically looks like a collection of Cooper pairs, which are electron hole pairs. In this case, they're neutral objects created out of the vacuum, which consists of essentially an empty layer of electron, an empty Landau level in one layer, and a filled Landau level in the other layer. Gradients in the phase, which are important for the dynamics of what goes on in the system. In this case, gradients in that phase, much the same way that they behave in superconductors, gradients in that phase correspond to currents, but not currents of electricity, currents of excitons. Okay, so again, and this, I mentioned this already earlier on. There are two transport channels, really, because there's a gap and there's a condensate. There's parallel transport, where I drive current in the same direction in both layers. Though there are excitations above the energy gap, they're complicated vortex-like objects. I won't have time to really talk about them, but they're the things that are they move on the edge. They're the things that are responsible for the simple effect of, I see a quantized Hall plateau, I see resistivity dropping to zero. But there's also this condensate. And the condensate is this transport of excitons. Excitons are neutral. So if I move the excitons from left to right, as in this cartoon, it really is equivalent to electrical currents flowing in opposite directions in the two layers. That's different. That's fundamentally different than this. So counterflowing electrical currents are carried by, we think, are carried by excitons. They're neutral. So unlike the charged excitations, they're not confined to the edge. They should be able to move through the bulk. They should be dissipationless at low temperatures. To do experiments, I think the most interesting experiments are those which are done, which probe the condensate in one way or another. One way to do that is to literally, even though they're very small tunneling, you can always measure it if you want. And I'll talk about this extensively tomorrow. Drive an electron from one layer to the other, and somehow you leave a void behind which has to get filled in, and you make an excess and the other layer has to go out. So you can see with these cartoon arrows that that's a counterflow problem. Similarly, if you literally drive currents in opposite directions in the two layers, you should be able to see cool things. And we'll see whether we do or don't as we go on. So let's start with a measurement which takes us back a little ways. And I think this was the first measurement, maybe not the first, but it's one of the early transport measurements, not tunneling, just transport measurements that illustrated something exotic was happening at filling factor 1. And to introduce that, I'm going to talk about the subject of Coulomb drag. Coulomb drag is simple to understand, or it's simple to imagine. I have two layers, maybe two pieces of tinfoil, and I drive a current through one piece of tinfoil, and I have another piece of tinfoil that's close by, and I try to see if any voltage develops in that, and it's isolated. It's not electrically connected to the to the current carrying layer. So normally you'd say, well, I'm not going to see anything. Well, maybe if they're really close together, you see something, and indeed, won't work with tinfoil. You have to be too close. But if you do it with gallium arsenide two-dimensional electron systems, lo and behold, a voltage does appear over there. And that voltage is very strongly temperature dependent and tells you about electron-electron interactions between the layers. Electrons in one layer scatter off of electrons in the other layer and push them along and create a force that produces a voltage. Now, if you have a magnetic field, you have to sort of generalize your thinking about this. Of course, there's the same thing I just described, that type sort of longitudinal measurement, but there's also a Hall measurement you could imagine making. And drive a current in one layer, and I've got a magnetic field applied, so maybe there's a Hall voltage in the other layer. And you think about that for a minute, and you say, well, that can't be, because to get a Hall voltage, I need a sideways force. To have a sideways force, I probably need a Lorentz force, but there's no current in the blue layer, so there can't be any Lorentz force, so there's not going to be any effect. That argument's not watertight, but in most situations, it's darn close to watertight, unless there are strong correlations between the layers. So let's do an experiment on the gallium arsenide system. This has now been seen in graphene as well, but it was first seen long ago, really, 2002 or 2001. 20 years ago. Here we are again, measuring the transport in our double layer two-dimensional electron gas. And this red curve is just the ordinary rho XX Longitudinal resistance, nothing to do with drag, shows a nice deep minimum at filling factor 1. Now I measure the drag, the longitudinal drag, which measures scattering between the two layers. Sort of, you can understand that qualitatively. And you find out that, number one, it exists. You can see it. It's pretty strong, actually. But it vanishes at the same place that the ordinary resistance vanishes. You say to yourself, that's not a surprise. There's an energy gap. I would expect that. And so maybe I haven't learned too much that's really dramatic from seeing that longitudinal drag. Turns out it's remarkably large. Those peaks are pretty big, but it wasn't a surprise to see that. This was a surprise when we measured the Hall effect in the layer that is not carrying any current, or so we think. There's a big Hall drag, really big. And in fact, it's so big that it reaches some kind of plateau. And you look at the plateau, and this was work of Mindy Kellogg, student of mine. It was 2002. I wasn't sure I could remember it right. She found out that it was quantized to h/e². And I can tell you, we got a lot of pushback from the referees on this result, that this couldn't be true. Or if it was true, it was because of some experimental problem that we had that we didn't recognize. So we argued about that for quite a bit with the referees. It's even stranger than you might imagine. If you keep looking at this and you say, well, what's happening to the Hall effect in the layer that is carrying the current? Well, you find out the layer that is carrying the current also goes to h/e² Hall resistance. Oops. They both have the same Hall resistance, and it's h/e², not half of that or twice that. It's h/e². And it turns out it doesn't even matter how much current is flowing in one layer or the other. If you make the same currents in both layers, you still get h/e². If you make all the current in one layer, you still get h/e². If you make 80% of the current in one layer and 20% of the current in the other layer, you still get h/e². It's just always h/e². This was very amazing. So let's talk about this. So in a drag measurement, again, as I said, current flows only in one layer. At least you're doing your darndest to make that be the case. But you remember now that in this excitonic state, that's not really one of the standard transport channels. Not that if you like the normal modes, or I don't know what word you want to use for them. You either go parallel or you go anti-parallel. So if this current's only in one layer, maybe the best way to think about it is, well, it's 50-50. It's partly currents going in parallel in both layers and partly a counterflow that adds in one layer to give you a net current, which is the actual applied current, and cancels in the other layer to give you zero. And if that's the case, then you could say that the quantized Hall experiment demonstrates the existence of counterflow. Okay, it's a nice story. Might be right. So you have to really do other experiments. What this tells you is that it would be much better if you made an experiment where you actually literally drove currents in opposite directions in the two layers, rather than trying to do this drag experiment. So we did that. Again, this was Mindy Kellogg's thesis work. And she drove the current down left to right in the blue layer, right to left in the yellow layer, and measured the Hall resistance and the longitudinal resistance. I'm not going to bother showing you. And if the layer separation, again, by this tuning technique, if we made the layers effectively far apart, there was nothing very interesting happening at h/e². At filling factor 1. On the other hand, if she let the layers come close together to go below the critical point, this red dot, the Hall resistance vanished. Okay, it vanished. So here you are. You're at this high magnetic field, a few Tesla, and you're measuring the Hall effect in a low dimensional conductor where in all other systems you know of, there's going to be a giant Hall effect. There's no Hall effect. And somehow it's because these two layers are close together and because the currents are flowing in opposition. So this was extremely exciting and sort of told us this counterflow picture makes sense. Now, excitons are neutral, so it's no surprise that the Hall effect will vanish if you drive only excitons through the sample. They're neutral. Yes, the positive charge in one layer maybe feels a Lorentz force, but it's tugged on by the negative charge in the other layer or vice versa, and the net force is zero, and so there's no Hall effect. But this was exciting. However, and I think, we maybe didn't understand this as well as we should have at the beginning, but there's really no way that this experiment tells you that those excitons are traveling through the bulk. If they're neutral, they're not confined to the edges. So maybe they're in the bulk or maybe not. I mean, you got to do something else to figure that out. Do you understand this point? The edge channels are there and how they influence when you've got contacts only on the edge, it's hard to know. It's impossible to know what's going on in the bulk, really. So for that, we turn to a different measurement. And maybe some of you aren't quite as familiar with this geometry as the standard Hall bar. This is something called the Corbino geometry. The Corbino geometry is a multiply connected geometry, donut, topologically. A donut is the simplest example. I have two contacts on a donut, but they're on opposite edges. So there's no edge state that connects those two contacts. And this is just data from a single layer two-dimensional electron gas. There's nothing exciting about this data. It's the conductivity measured between the two black dots. And you find out that as you raise the magnetic field, it makes all the quantum oscillations. And every time you expect there to be a quantum Hall state, you find out that the conductivity goes to zero. It's just what you expect. That's the signature of an insulating bulk. And that's, the essential ingredient to the quantum Hall effect is that the bulk becomes insulating. So the conductivity vanishes here at nu equal 1, nu equal 1/3, so on. It's all perfectly understandable. What we want to do, though, is we want to do the same kind of experiment with two layers. And for this, the pictures are going to get a little confusing now. So just bear with me a little bit. I'm going to have 4 contacts on these experiments, at least 2 on each layer, 2 on the inside rim of the donut and 2 on the outside rim of the donut. I forgot to put in a picture of the way the sample actually looks, but it looks pretty much like a donut. It's pretty much like this picture. Not exactly. And this work, actually, Corbino experiments really started in the Stuttgart group in 2008, and we picked them up a couple of years later. Okay, and for the purposes of what I'm going to talk about to go on, rather than drawing these donuts all the time, I'm going to draw them in cross section like this. But I want you to understand that the contacts on one edge, say the right hand side over here, are not connected by edge channels to the contacts on the left. And that's crucial. Okay, so let's do the usual measurement. Put a voltage or try to drive current from the outside, let's call this the outside rim, to the inside rim in parallel in the 2 layers, in parallel. Well, in the quantum Hall effect, there's a lot of different quantum Hall states. And then you reach filling factor 1 at nice low effective layer separation. So we knew that we would be in the condensed phase if we were at this effective layer separation, nice low temperature. It vanishes. Quantum Hall effect. It had to. So this didn't tell us too much, except that we weren't crazy about the geometry. All right, let's do the experiment a little differently. Let's take our 2 contacts on the left and connect a battery to them and see how much current flows. I don't have anything connected on the right yet. And this is a geometry which would like to drive tunneling currents from one layer to the other. And in fact, it does. And I've actually done a trick here to get rid of that tunneling or to greatly reduce it. And I'll have to ask you to come back tomorrow to find out what it is I did. But bottom line is I tilted the magnetic field. I kept the perpendicular field component the same, but I added a parallel component. It turns out that suppresses the tunneling by orders of magnitude. And so I did that. I did that on purpose because I wanted to get rid of tunneling. Okay. So we can go back to this and we look at this blue curve and we say, oh, there's some current flowing out at 200 microvolts or 300 microvolts for the battery. You can see something, but not much. And now over on the right, which again is on the other edge, the inside edge, let's say, of our Corbino device, I'm going to short them together. This is like the cartoon that I told you about at the very beginning. Remember the orange rectangle or orange square, orange diamond, the contacts around? I'm going to add a contact to connect those two layers together. But it's remote. It's not on the same edge. And now current's flowing. And it's really flowing. There's some nonlinearities in it, which we could talk about if you really want to. I don't know too much about them, but I could tell you a little bit about them. But somehow by doing something remotely through an insulator, I caused current to flow. This is exactly what I showed you in that cartoon. So it's kind of paradoxical, right? In this upper situation, no current is flowing. In the lower situation, lots of current is flowing. So is this counterflow through the bulk of the sample? The only way you can figure that out is you have to go measure the current that flows here through the shunt. Because maybe somehow by connecting them over there, the tunneling got turned on and I didn't know what I was talking about and something happened that was out of my control. Well, we went over there and measured that current, I sub S, and we found out that it was the same to within good accuracy with the current that the battery was actually delivering. In other words, the current really was going across the bulk in one layer and back across the bulk in the other layer in order to support this phenomenon. The only way to understand that is through counterflow across the bulk, even though the bulk is insulating to parallel currents. If you don't remember anything else about this talk, remember that. Okay. So what's the mechanism? So let's draw a cartoon. This is work that, or what I'm about to say is heavily influenced by work that Alan McDonald and his students have done over the years. If I have two layers that are somehow independent, connected to two layers, the same two layers, but are now in the exotic condensed phase, and believe it or not, you can create that geometry by using those gates that I told you about. I can send in an electron like so. And it can get retroreflected, as in Andreev reflection. But retroreflected not as a whole and not in the same layer, but as an electron in the other layer. And in so doing, it launches an exciton at the boundary. So let's see it again, right? Goes in there, boom, creates this exciton, which moves across the bulk. So something along those lines is what we think is going on. And that process, the details of that process, well, they're beyond my ability to understand. I've tried to understand them and I've thought about it, read a lot of work that Alan's done about it, but it's not so simple. But that's fundamentally, this Andreev reflection is fundamentally the process. So what I've told you then is that this experiment works. This I call this series counterflow. I'm driving currents through an external remote resistor by virtue of transport of excitons across the bulk. I can do another experiment though. I can, looks very similar, but it's not. I put a voltage between the two contacts on the same layer, this green layer, and I try to drive current there. And I measure drag, or if you like, the voltage on the other layer, again, with tunneling suppressed. And if this exciton picture is right, and that's the only thing that happens, then I think you can see that the currents have to be equal. If I transport some excitons, it's transporting the same amount of magnitude current in both layers. So we ought to try this experiment and see whether we get the right result. And did that. I should say Debalina Nandi and Aaron Fink did this experiment. This is called Corbino Coulomb drag. This is the ratio, or not the ratio, this is the current in those two situations, the current I1 and I2 as a function of voltage. In the condensed phase, I should have written down some more details here, at low temperatures, low D over L in the excitonic state. And we find that if the voltage is not too large, say below 200 microvolts, those two currents are the same in magnitude. They're opposite in direction, but they're the same in magnitude. So this drag picture is consistent with this bulk transport of excitons. However, as the current goes up, as the voltage or current goes up, the two curves separate from one another. And it's important to at least have a qualitative understanding of why that breakdown is occurring. Here's a graph of the ratio of those two currents as a function of voltage at different temperatures. If the temperature is low, say here at 17 millikelvin, it's very nearly 100%. Again, the signs are opposite, but I should have put some absolute values on this, but it's equal to 1. But as the voltage goes up, it falls away. That's just what this was showing you. It falls away. And at higher temperatures, it does so right away. It's already, even at the lowest voltages, the currents are not equal. And as you go up in temperature and leave the exotic condensed phase, the current in the drag layer just goes to 0. You don't see anything. Okay. So again, going back to this picture, how do we understand that? Turns out it's pretty easy, really, at least qualitatively. If we make a model in which we have a battery and some external resistors, because believe me, there are always external resistors, plus there are resistances associated with the quantum Hall effect itself, but let's just call them R1 and R2. And I put a voltage in one layer and I look for current and I measure the current that flows and I measure the current that flows in the other layer. If the system is a superfluid of excitons, this is a theoretical assumption, and the bulk conductivity to charge, right? I mean, you're in a quantum Hall state, resistivity is very low. It's only low insofar as, I mean, it's never truly 0. It's always some conductivity in the bulk. But if we assume it's 0, then you'll very quickly conclude that these two currents have to be exactly equal. And their magnitude, you could say, well, how big is the current? It's just determined by the external resistors. Turns out it's just determined by R1 plus R2. Okay. Otherwise, it'd be infinity if there weren't any. It would be infinity if there weren't any resistances in there. And as I said, these two resistors can't be, the sum of them can't be smaller than, I think, twice H over E squared. Okay, so that's not what we see because, right, it's go up high in temperature, or if you go up high in voltage, the ratio is not unity anymore. So what do we have to change about this model? The simplest thing to do is point out that, well, you know, the parallel conductivity for charge isn't really 0. It's just small. And moreover, it depends strongly on temperature. I showed you that a long time ago, that there's some thermally activated dependence. And that conductivity has to be included. And that conductivity allows for net charge to flow across the system. And so you can generalize this model. It's a kind of simple thing that we did. And you'll find that the ratio of the two currents is determined in this model only by that residual conductivity which exists in the charge channel. So it's just call it a parasitic effect, if you like, a nuisance effect maybe. But it's important to be able to identify what it was, and we did that. And in fact, if we made models, we could go back and measure in the Corbino conductivity more carefully as a function of temperature, as a function of voltage, and so on, and then put it into those formulas that I just showed you. We could actually predict with reasonable agreement with how much these two curves should deviate from one another. And not perfect, but pretty good. And the temperature dependencies we got pretty darn well here at 0 voltage. I should point out that, I guess I said this, but the conductivity in the charge channel obviously goes up if the temperature goes up, but it also goes up if the voltage goes up. Put a lot of voltage across a hall bar, current wants to flow. Okay, so excitons transport energy, but they don't transport charge. And they do it by this funny process of this Andreev type process. It's very interesting. It kind of reminds you of, I used to sometimes show a picture where I had these two things as two superconducting wires. And I would drive, say I have a transmission line and I want to drive electricity from Los Angeles to New York. And I have two wires that are superconducting all the way. And they would transport, one would send the current from LA to New York, and the other would return the current from New York to LA. And this exciton condensate, if I could have it stretching all the way from LA to New York, and the current, and it was at 25 millikelvin, and the current was incredibly small, we might also be able to transport electricity with just one superconducting or one exciton condensate. So the question is, for this, the physics question that's important here is this transport really dissipationless or not? And this is a question which is not answered. I mean, I can tell you right away, it's not known. We know that the colder we get, the better the sample, the less the dissipation is. But I believe it's true that I guess I'm not so knowledgeable about the graphene case, but certainly in gallium arsenide, there's always a little dissipation. And we tried to measure that. Well, in this geometry, we couldn't do a very good job of it. And so the blue curve is merely an estimate based on independent measurements of how much these voltages should be, how much the current should be. And it almost matched what we observed, but the estimate was not perfect and it didn't match perfectly. So yeah, the dissipation is small, but it's not possible to really say much more than that. Alternatively, one can go back to the experiments done in the simply connected geometry, the so-called hall bar geometry, and from a variety of such measurements, determine two different conductivities. One for parallel transport, which is thermally activated, becomes smaller and smaller as the temperature goes down. That's standard quantum Hall physics. And invert the measurements of the Hall resistance and the longitudinal resistances in counterflow and use it to establish something we would call the conductivity due to counterflow. And that goes up and up and up as the temperature goes down. So that at the lowest temperature, there's 7 or 8 orders of magnitude difference in the conductivity for excitons through the bulk and the conductivity of charge through the bulk. They're different by many orders of magnitude, but it ain't infinity. It's even so high, the conductivity, that exceeds the conductivity of the system in the absence of any magnetic field at all, which is where the conductivity normally you would expect to be the absolute largest. So it becomes very, very large, but it's the best that we can do to say that there still is some residual dissipation. And there's been a lot of theoretical work about what that's coming from. I'm not going to talk about it. I don't really, I'm not sufficiently knowledgeable to talk about it. So let me just conclude. I think I've pretty much used up an hour. Bilayer quantum Hall systems, filling factor 1, they do host a very unusual quantized Hall phase, which contains a condensate. That condensate can be viewed as a ferromagnet, if you like, but it can also be very nice with nice intuitive appeal, thought of as an exciton condensate. We've demonstrated, I think, quite clearly that the bulk of the system, as all quantum Hall states are, is opaque to charge, but it's transparent to excitons. And that exciton transport appears to be weakly dissipative. I'll have a little bit more to say about that possibly next time. What the nature of that dissipation mechanism is remains to be decided. Some of the questions that I think are important to think about is there really phase coherence to this system, quantum phase coherence? And if so, on what length scale? Can we see that experimentally? Can we make an excitonic Josephson junction? Something we've not done. Where else does this view graph's a little bit old. Where else does this phenomenon occur? Well, these two topics, Professor Halpern will have lots to say, I think, about where this kind of phenomenon occurs elsewhere. And I'll say more tomorrow, about what happens, what we can learn about exciton coherence. So let me finish with this last slide. So as I told you, ideas for exciton condensation are quite old, right after BCS. Here's an example of a paper in Physical Review that talked about it. And I have this notable quote from the paper that I like very much. Since excitons are electrically neutral, we cannot expect to detect such condensation with spectacular electrical effects. And that's just false, as I hope I've tried to convince you. All right, so thanks very much. And I'm happy to take any questions that you might have.
Thank you for the wonderful talk.
You're welcome.
All right, let's go through some questions. So the first question is, naively thinking, an exciton should have a short lifetime since it is created from an excited state, for instance, a particle-hole pair that can annihilate. What determines the lifetime, and when is it stable enough for all the phenomena that follow, like exciton condensation?
Okay, so that's a good question. So here's what I know about that. In the case of, let's say, the traditional way of creating excitons, what do? You shine light on a sample, and you kick an electron out of the valence band into the conduction band. The hole is left behind, and this object is an exciton, and it recombines. There's a big energy difference, and it recombines, and sometimes emits light, and very interesting. Happens maybe in a nanosecond, very quickly. On the other hand, if you're a good quantum engineer, you can design a sample in which the electron layer and the hole layer are separated from one another. Leonid Butov, for example, at San Diego, spent many years working on that, and can increase that recombination time to a microsecond or maybe even more. I don't know what the latest is on it, which gives you some hope that in that microsecond, after you shine the light on, those excitons could cool down and do something collective, like condense, Bose condense, and then you could detect that. And he's done a lot of very beautiful experiments on that, but it's really hard because of this recombination. The system that I described does not do that. These excitons are stable. They do not recombine. I suppose you could talk about a recombination time if the tunneling would be regarded as the mechanism. But really, I can have these two half-filled layers with some substantial layer separation between them. And this system is perfectly stable. These excitons, their Fermi levels are together. There's no energy gap. This system is completely stable. And these excitons, if you like, last, quote, forever. So that's really, in many ways, the beauty of this system. These excitons are created by virtue of the magnetic field, converting, if you like, the half-filled layer of electrons in one of the layers, allowing you to think of it as a half-filled layer of holes, and having the other layer be half-filled layer of electrons. And so you have these excitons and they're stable.
All right, thank you. So the next question is, can filling factor 1 be explained by 1/3 plus 2/3 instead of 1/2 plus 1/2? in the two layers?
Yes, it can. I didn't talk at all. I don't know whether Professor Halpern will talk about that or not, but one of the interesting direction space for this problem is to make the layer densities unequal, but have them add up to be equal to 1. And it turns out that certainly for small layer separation, we call it imbalance. For small imbalances, the system is completely indifferent. There's just some quantitative changes, but it's perfectly possible to have the system have an exciton condensate at 1/3 plus 2/3. However, as you rightly point out, whoever asked this question, there's somebody else waiting around at 1/3 plus 2/3 saying, well, maybe I'm lower in energy. Let me be a Laughlin 1/3 state in one layer and a Laughlin 2/3 state in the other layer, and forget about interlayer correlation. That's certainly possible. And in fact, and it's really a question of competition of energies. Who will win? If the layer separation is really small, I think the exciton wins. If the layer separation is large, clearly 1/3 plus 2/3 fractional quantum Hall states independent in the individual layers will win. And we did, in my group anyway, we did an experiment maybe almost a dozen years ago, 10 years ago, in which we examined the effective layer imbalance, and were able to show that that was near the boundary of how far we could push the system for various experimental reasons. We could show that there was a situation in which the phase boundary was perturbed by the nearby proximity of the 1/3, 2/3 fractional quantum Hall states, as opposed to the 1/3 plus 2/3 equals 1 exciton condensate. So it's a great question, and it's absolutely, I mean, in principle, right? What's wrong with 2/5 plus 3/5, or so on and so on? There's all these different possibilities. So really, the phase boundary probably is some very complex structure in the limit of no disorder and zero temperature. This probably quite complex. And a little bit of that has been looked at, but not a lot yet.
Okay, thanks. The next question is, why is the magnetic field needed? It seems that the Hall and the electron move in opposite directions under the magnetic field, and this does not favor the pairing between them.
I'm confused by that question. So again, you don't have to, if you don't like this picture, probably the best thing to do is to simply say, I've got two layers of electrons, and they form this phase in which the system may be regarded as a ferromagnet. The electrons lose their memory, if you like, of what layer they're in. You don't have to think about these holes, but it's perfectly fine to use that picture or to talk about the system as though you've made this, it's just a theoretical device, as though you've made this electron hole, this particle hole transformation on one of the layers, and start talking about the holes as opposed to the electrons. That layer in which you talk about the holes also contains a fully filled shell or fully filled Landau level of electrons that give it its Hall, that gives the system its net Hall resistance of H over E squared. But what's left over are these excitons, which are bound electron hole pairs.
Okay. Then, so as the BCS-like wave function for the exciton condensate is written here, can one also talk about a U1 symmetry breaking for the exciton condensate? If so, what will be the physical picture for a U1 symmetry breaking for the exciton condensate?
So that's I would say beyond my pay grade to have much to say about that, but I will say something about it tomorrow. So I'm not going to answer your question. There is a U1 symmetry breaking that takes place in this system, and it leads to a linearly dispersing Goldstone mode. And I'm not going to say anything further about it right now, because I want you to come back tomorrow and see how we have detected that mode. I didn't say a word about that today. I avoided, which to what in my view is every bit as spectacular physical phenomena to these transport measurements that I highlighted today, in plane measurements, are the perpendicular tunneling measurements between the two layers, and that's where you can grab hold of that Goldstone mode. And so I'll definitely talk about that tomorrow.
Come back tomorrow.
Yeah, come back tomorrow. I don't want to spoil. I don't want to steal my own thunder for tomorrow.
All right.
Anything else?
Has bilayer quantum Hall been realized experimentally in topological churn bands without a magnetic field?
Oh boy, don't know. I'm going to just be honest. I don't know the answer to that. It's certainly some thing that people talk about, but I'd be foolish if I waded into that with an answer.
All right. Since mobile interlayer excitons will generate counterflowing layer currents, can intralayer excitons do something similar?
That's an interesting question. So by an intralayer exciton, I think of an electron hole pair of some type occurring in a single layer, and that's a neutral object. So I don't know how you would talk about that in the language of currents flowing through a single layer. So I guess I don't know any more to say about it than that. Because obviously, I mean, in a sense, what we're able to do with these bilayer systems, and I didn't talk about this. I'm hoping there are some experimentalists out in the audience, but you have to ask yourself, how do you get a hold of the two parts of a Cooper pair separately? And that's what we're doing. If you think about it, we're grabbing hold of let's call them the holes in one layer, because we can make an electrical contact to that layer and that layer alone. And we can grab a hold of the electrons in the other layer. These are the two. And that's why this last view graph, why these fellows could not possibly have imagined that we could do such an electrical experiment, is that we can essentially make a connection to each half of the pairing, the object which is paired. It's, if you could do that in a superconductor, that'd be pretty cool. But in this system, because of the physical separation of the layers, you absolutely can do it. It was a tremendous, it was a huge experimental challenge in the gallium arsenide case. It turns out in the for reasons of I don't need to go into, but it was very hard to do that. But we succeeded eventually. In the graphene system, in a sense, it's much easier, because what you're doing in the graphene system, you're taking these two very thin, think of them as little pieces of tinfoil. You lay one down, you put down an insulator, you put some paint on it or something, and you lay down another one. And they're crossed like this. So making a contact to one layer on this side and this other layer on this side is easy. You can't do that in the semiconductor heterostructure geometry. You have to come up with another way of doing that. And we did it. And these experiments were one of the results of that ability. So for an exciton, an intralayer exciton, I don't see a pathway to doing that. Maybe there is one, but I don't see it.
Oh, this is a question that I also had. So how can the exciton flow in the insulator, and how is it different from normal electrons? Because I guess the electrons and holes still live in insulators.
It's neutral. It's neutral.
Okay.
What's to prevent it from? I could ask the question in reverse. What stops it? Why doesn't charge flow in the bulk? Is that the Fermi level is in some gap for an ordinary quantum Hall state. There's plenty of electrons, but they're immobilized, right? The only way you get current is with stuff happening at the boundaries, as Professor Halpern talked about in his first talk. You can make imbalances on the edges and get currents to flow, but not through the bulk. But these excitons don't have to have that restriction. And I think, as I've tried to say, is I think this observation that the system is transparent to counterflowing currents. Number one, it's experimentally proven. It exists. You don't have to talk about it with excitons. You don't want to, but I am able to get these physical currents to go across the bulk as long as they go in opposite directions. And in fact, one of the challenges I think in trying to assert whether or not the system is truly dissipationless in the exciton channel is that how the heck do you really make sure the currents are in counterflow? Well, they might be, overall magnitudes might be held to be very nearly identical, but how about the direction? Well, the two currents are like this. Well, they're opposite in direction, opposite in magnitude, but they're clearly not in counterflow. They're only in counterflow if they're like this. So if your geometry is such that the currents, and because A, your geometry, and B, because samples aren't perfect, they're full of disorder and inhomogeneities, maybe there are regions where there are currents being forced to flow out of counterflow, and those are dissipative by definition. So that's a challenge, and I think it's something that we worked on pretty hard in developing geometries, which at least from a geometric point of view, the currents were going to be flowing very nearly in both equal in magnitude but opposite in direction. So we chose very long, thin geometries and tried to finesse that, but issues associated with inhomogeneities, those are kind of almost out of your control.
Okay, thank you.
You're welcome.
And then the next question is, some old theoretical discussion on superfluidity argued that due to a missing off-diagonal long-range order, exciton condensate does not have superfluidity. Do you have any comments on that?
Well, I've heard that statement, and I'm not going to comment on it. I'm going to let Bert comment on it tomorrow in the next talk if he wants to. So there is an important thing that I didn't describe. I didn't say anything about, and I'm not sure that it's the correct thing to say here, but I'll say it anyway. And maybe it'll get corrected by someone else. It's never true that this system doesn't have any tunneling. No matter what I do, the quantum mechanics doesn't just give up and go away and decide not to tunnel from one layer to the other. There's always some finite amount of tunneling. And in fact, that tunneling in principle disrupts the statement that the system is a superfluid. It's really, aside from other reasons why it might or might not be a superfluid, in the presence of tunneling, the phase is not free to simply wind the way that it would if the system were truly a superfluid. So whether or not that tiny, part in 10 to the 7th that I told you about, whether that was the operative reason for why we didn't see a perfect dissipationless flow or better than what we did see, I don't know. But I think it's kind of an in principle thing because I can't get rid of that no matter how hard I try. It's always there, and it's true in graphene as well as it's true here. So there's a problem with that. I was once one likes to remember amusing remarks by referees. And I remember a paper that Alan McDonald and I wrote where we talked about this problem. And the referee, who I now know who it was, and I'm sort of grateful to him for this comment. He said, one cannot be a little bit superfluid. And some of you will understand that joke and some of you won't, but it's true. You either are or you aren't, and we aren't. I'll be really literal about it. We aren't.
All right, thank you.
Sure.
Then, is it possible to observe exciton condensation at higher Landau levels or even in the lowest Landau level, but at total filling equals 3?
The answer to that is something which has annoyed me for 20 years. The answer is yes. And the thing that annoyed me is we don't see it in gallium arsenide, and it is seen in graphene. And so I think I will leave that to Bert to talk about. We searched very hard, as did Kosfod-Klitzing's group in Stuttgart, at filling factor 3, because 3, the proper symmetry here is 3 is the same as 1 and 2. It's just like, nu and 1 minus nu and nu and 2 minus nu. The symmetry in this case, but with double layers, is between 1 and 3. And search though I did, and my students and Klaus's group, and we never found it. Meaning our samples just didn't do it. There's some reason, and we don't know what the reason really is. There were always little hints that something was getting ready to happen, a little fluctuation in the resistance, but it never turned into anything. And that's not true, as I understand it in graphene. Now, higher Landau levels still, that's even asking too much. Maybe, I don't know. Should be, right? You could imagine it. You could imagine 5 halves plus 5 halves. Who knows? But I don't know that there are any, even in the graphene case, whether there's stuff that occurs in higher orbital Landau levels. That would be called exciton condensation. Good question, though.
Great. Can you measure effective charges, which are expected to be 0?
So I have not made any attempt along those lines. So as you know, in this case, yes, the excitons are neutral, or supposedly neutral. There are charged excitations in the system, though, as well. The things that live on the edge channel, in the edge channels. And those objects presumably can be detected via noise techniques analogous to the ones used in fractional quantum Hall effect, say at 1/3 filling, where you see these, shot noise that gives you some signature. Those have, it turns out that, at least from a theoretical point of view, the dominant excitation has charge 1, not charge 1/2 or anything. It's a complicated, I showed a picture of it and went through it very quickly early on, that there are vortex-like excitations in the phase field that are known as merons and antimerons, and they're paired up in pairs of opposite vorticity. And although the merons themselves have charge 1/2, you always have 2 of them, and so there's charge 1. So presumably somebody could go do that and see those. But as far as seeing the 0 charge, the neutral objects, I don't know. Good question. I don't know. I can't answer that. I don't know.
At the lowest tunneling strength, there is no 1/2 plus 1/2 quantum Hall effect. It seems that this state still needs finite tunneling, ?
I don't know where that impression came from. In our experiments, all that I showed you was data taken in samples that had the lowest possible tunneling strength that we could measure. This part in 10 to the 7th of the Coulomb energy that I mentioned. And that system, if the layers are close enough together, which is obviously, got to have, and the temperature is low, yeah, it does. It has this quantum Hall effect. And there's no evidence that I know of that in some still lower regime of tunneling that this effect goes away. The belief is that it's basically the energetics are completely independent of tunneling in that regime, as long as the layer separation is small enough. So I'm not sure where you got the impression that it went away at 1/2 plus 1/2. It does not, if they're close enough together.
Why is D over I about, or D over L
over L.
2 on the tunneling, when the tunneling strength equals 0?
Good question. Very good question. Here's what I know, which isn't very much. That's what we observe. So you don't like it, too bad. That's the way it is. The other is that in theory, there's been a lot of numerical work, maybe Bert will talk about this, I don't know, that suggests that for very thin layers, which we don't have, I didn't talk about that, but we have these electrons in quantum wells, and the quantum wells themselves are 18 nanometers thick. So the electrons are not particularly, they're in the lowest state. So they're definitely two-dimensional, but they're fairly fat. And as a consequence, the Coulomb interaction between particles is influenced by that fatness. They're not point objects. But in theory, you can talk about it as though you can pretend that they're perfectly ideal and they're just two-dimensional points. And if you do that and you do numerical work there, I believe that theoretical estimates place the transition closer to D over L around 1. So we see it at closer to 2. What's going on? I personally believe this is almost entirely, I would like to say it's entirely due to theorists being wrong, but I can't do that. I think I can say, though, that it is strongly influenced by the finite thickness of the electrons. And in support of that statement, I will say that in some experiments done at Princeton in the earlier mid-90s by Mensur Shayegan's group, they looked not at double quantum wells, but at quantum wells which were single quantum wells, but very fat, like 600 angstroms fat. And when you have a system like that, the wave function of the electrons tend to be sort of bimodal. It's not really zero in the center. It's as though the tunneling is really strong, but the electrons are monstrously fat. So it's hard to know, how to compare that to what I've talked about. Nevertheless, in those type of samples, the onset of the nu equal 1 Hall plateau occurs at D over L of around 6, as high as 6. So much, much bigger. That's what I know. We've done a very limited amount of study of samples that have slight variations in thickness. And in those, not only thickness, but the ratio of the thickness compared, it's not just the intra-layer Coulomb interaction that's affected, but the interlayer interaction is affected as well. And you can see that if we have very little data on this, but if we make the layers thinner, the critical separation does go down a little bit, tiny bit. So I think this is a finite thickness effect. Be interested to see if Bert has any comments on this. We'll have to wait and see. But you're right, it's 2, not 1 or 1.8, something like that.
Or just have a few more. Thanks for answering all these questions.
Sure, no problem.
If you apply voltage on both edges rather than shunting one end, will you also measure currents?
Both edges. Isn't that what? Oh no, hold on. Oh, I know what you mean. So in this upper diagram, suppose the resistor on the right was a battery. Is that the idea?
All right, that's what I think this person means.
Wait till tomorrow. Wait till tomorrow. I'm going to tell you exactly about that situation. It's really cool. It's really, really interesting what happened. And it tells you something about the coherence of the excitonic phase across this dimension from left to right, by the way, is fractions of a millimeter. It's a huge distance compared to interelectron spacing. So they communicate with one another, and you learn something deep, I think, about interlayer correlations and their coherence. So please wait till next time, because the answer is, yeah, there is something cool there.
Yeah, come back tomorrow.
Okay, come back tomorrow. Sorry to put you off like that, but I want you to come back tomorrow.
Okay, I think the last question we have time for is, why do interlayer excitons travel freely without being trapped by disorder?
Well, they're neutral. Now, so disorder is going to be much less important than if you have some long range potential. And how big are these objects? Nobody asked that question. How big are they? Well, roughly speaking, the size of them is given by the separation between the layers. There's a couple hundred angstroms. like 20 nanometers. That's a small number compared to what we believe typically are the potential fluctuations. So you might think, that object's pretty much going to be viewed as neutral. That doesn't mean that some excitons aren't trapped and in fact ionized. There is some belief that in fact there are trapped vortices in the system. And those trapped vortices, single trapped vortices, may be responsible for the dissipation that we do observe. It's a good question. Not too much known about it, at least not by me.
All right. Thank you so much.
Sure, I really appreciate having the opportunity.